a few more teams left, so we're up to team number 13, Lucky 13. Now they've got a pretty mysterious name, Team Shadows, I believe, right? Team Shadows?
That's us.
Team Shadows.
I'll even put on the screen in a moment.
Yeah. So while they're plugging that in, they are going to be presenting their idea, which they've labeled here as serendipitous stellar occultations.
Yeah, so that's the technical name. If you're going looking for it on the internet, that's a good place to start. So,
all right, so Team Shadows then. Go ahead.
Hi everyone. I'm Andrew, and I'm part of Team Shadows, and we're searching for small asteroids, aka serendipitous stellar occultation. So that's going to go long. So, firstly, small asteroids. What do I mean here? We're talking about asteroids that are around about 100 meters up to a kilometer across. Now, that sounds like a pretty big chunk of rock, but that's just peanuts compared to space. And these are really dim, so it's really hard to find them on optical scopes. They're just too small, too hard to track, and that's our challenge. So the problem is to try to find these ones. And so what we're intending to do is almost look at the opposite problem. Turn it around, do it the other way around. So what we're going to rely on is the tiny shadow that an asteroid casts as it passes between us and a distant star. So looking from the Earth's perspective, if you look out at the star that's been occulted, I think that's the correct term, then you should see momentary dimming. That's all you get. That's what we're working on. So how do we make this work? So what we're proposing is we set up an array of low power and affordable telescopes so that we can get enough of them and set them out over a reasonably large geographic area. And that way, get all of those telescopes pointing out to the same stars, the same range, and then aggregate all of those readings. And then if we can find 3 of them that line up in a way that would suggest an occultation, then hey presto, we've got an asteroid. And ideally then, perhaps we can get the big telescopes, the real expensive ones, and say, look, here, go and look at this part of the sky, you might see something. So the opportunity. These are really dangerous asteroids. If they turn into a meteor and they hit us, they're going to do an enormous amount of damage. If it comes over a populated area, it's really a disaster time. It's not end of Earth, life on Earth, but pretty bad anyway. So we want to find them before they find us. In terms of the, we've already heard about asteroid mining. If we can find more asteroids, then potentially we can find ones that are on much better orbits. It's much easier to get to and get back from, and that can save an enormous amount of money in the context of mining asteroids. So our target users in the early stages, we're looking at the amateur astronomers. They're the ones that've got the enthusiasm, they've got the equipment, and they've got the knowledge to take the observations in the first place. Now, what have we done this weekend? First of all, we have to prove that it works in theory, because if it doesn't work in theory, it's not going to work in practice, so we can pack up and go home. Unfortunately, we kind of made it work in theory, so we're going to have to go and do some more work on this. So first of all, simulating observations and noise, so we've got something to work through. And then the real crux of the problem is the search. So we've got what's an enormous search space, trying to find triplets of observations when there's a lot of noise. So for the computer scientists in the crowd, that's an order n squared problem. So if we don't get that right, or there's too much noise, then we might as well pack up and go home. So I think we can briefly show here's a simulation, one that we prepared earlier. Okay, let's move along. So the value proposition here, we're really trying to accelerate astronomy by engaging the amateur community and leveraging the scopes, the knowledge and the skills that they've got. What we've done so far, we've done proof of concept, we've managed to get it working in theory, we've produced a model, we've got a search algorithm that works, and we've started planning for the next steps. Speaking of next steps, time to get our hands dirty. We need to get field trials, get data, approach NASA to get reference information so we can calibrate and ensure that we're actually getting genuinely good information. And we're seeking volunteers to help with the field trial, to help with software development for the video capture, and making sure we've got volunteers with the right gear and help us scale up and get out into the field. So that's it. Briefly, the team, Ivan, Esteban, Lena, Sparky, and Katja. Thanks for any questions.
Thanks very much. Can you tell us a little bit more about the actual data model that you used?
Yes. The actual problem is the noise. Suppose you take a shot at the night. What you will see? You will see a very bad quality because there is noise on CCD metrics. So we're expecting like 10,000 noise events, and we need to find among them the real data. And the problem that we don't just have to look for events, we have to look for pairs. So we have 10,000 square 10,000, hundreds of millions. So we actually showed that we can work with this data. First, we filter them to reduce the amount of pairs. We take data on ages of our array. We sort them by time. Then we give a quick estimation of how good this predicts the events in between. By having this, we can detect it pretty well. And what is good that due to oversampling, because we have many rows and get many points of data, we get pretty good estimate of velocity of asteroid. And since it passes in front of a star whose position is known, we get an extremely precise estimation of its coordinates.
So I've got a quick question. How many of these asteroids are there? Like, so when you're scanning this, how many are you going to find every night?
Well, what's nice about this device that it just reaches in outer space. It will detect near Earth asteroids. It will detect asteroids in the asteroid belt. It will detect them in Oort cloud. If we're talking about near Earth, then there is about 1 million potential targets. If we have an ideal equipment, then we can expect to detect 1,000 of them per day. So we can, in several years, just clear most of them.